Welcome. This is Jim Corkins, and we are continuing on with energy. We are now in 5.1. Now, in our class, we are going to be dealing with mechanical energy. All right, it's different from types of energies that you're probably used to dealing in chemistry, where we're not really going to be looking at heat or chemical energy. This is all mechanical energy. And when I speak about mechanical energy, I'm talking about potential energy due to gravity, potential energy due to a spring, kinetic energy, and work. And work is a type of energy due to contact forces. But for right now, let's concentrate on potential energy and kinetic energy. Okay? Now, suffice to say, potential energy is a type of energy, and it's kind of a stored energy. All right? So if you lift up an object and you're holding it there, you've taken that object from a floor and you've added height to it, and now it's that height, you've used your muscles to raise it up that height, and now that energy is just held in place and waiting to fall. Okay? Another interpretation of that is if you pull a spring, okay, that energy is waiting to, that restorative force is waiting to snap it back to its original position. So I've heard new types of batteries where instead of, having a chemical battery, where in fact what you do is when you want to store electric energy, what you do is you raise water up to a height, okay, and that energy that you use to raise water up a height, you could then use later on, that excess energy you could use later on to power your cities at night when you're not using solar power anymore, and you can't use solar power. Okay. The other type of energy, which is kind of the whole point of this mechanical energy, is kinetic energy, and that's the energy of speed. So potential energy is due to gravity is the energy of height. The potential energy due to a spring is a stretched or compressed spring. Kinetic energy is basically the energy of speed or motion. Okay, if an object is moving, then it has kinetic energy. All right, and we already saw that kinetic energy had a 1/2 mv squared. So basically, if you are moving and you have a velocity, if you square that, well, now you're quadrupling the kinetic energy. Okay? So we're going to talk about all of these. All right? So the big overview of everything that we're going to go through is right here. Okay? And this is going to be essentially a really good equation sheet that covers everything that we're going to be doing in this energy area of 5.0 module. Okay. Now, we'll get into all the specifics of this. All right. We're going to start with kinetic energy. So like I said, kinetic energy is the energy of speed, and we saw how it was derived. Kinetic energy comes from work. So if you have a force applied to an object, that its velocity will change. And that change in velocity is also a change in kinetic energy. So let's go ahead and test our understanding of kinetic energy. Okay? Remember, K is equal to 1/2 mv squared. Now, suppose you have a car. You have two identical twins in two identical cars. And one car is moving 4 times faster than another car. Compare their kinetic energies. Which car has more kinetic energy than the other, and by how much? Okay? So here you have the one car that it's moving it's got 4 times the velocity of this other car, which is just 1 velocity. So obviously that top car is moving faster. Figure out which one has more kinetic energy and by how much 4, 8, 12, or 16. Pause the video now. Okay, well, if we take a look at this top car, and we could, let's say the top car is moving at 4 meters per second, and this other car is moving at 1 meter per second. Okay, now both cars weigh the same, and let's say they are 1,000 kilograms. Okay, so that means this top car is going to be 1/2, well, actually, kinetic energy is 1/2 mv squared, and this top car is going to be 1,000 kilograms, that's going to be its mass, times the velocity squared, which is 4 meters per second that we're going to end up squaring. Okay, the bottom car is going to be 1/2 1,000 kilograms times 1 meter per second that we're going to end up squaring. Okay, so let's figure out what each one of those are. Get my calculator up. So 4 squared was at 16. Actually, do I really need a calculator? So is this 16 divided by 2, which will be 8. 8 times 1,000 kilograms is going to be 8,000. So this top car will have the kinetic energy of 8,000 joules. The bottom car is going to be, what is that? 1 divided by 2. So this is 1,000 divided by 2 is 500. So this will be 500 joules. Now, if we compare those two things, if you take 8,000 joules and divide it by 500 joules, well, let's figure out what that is. 8, 1, 2, 3, divided by 500, 16. So the top car has 16 times more kinetic energy than the bottom car. Okay, so the correct answer was 4. Right? Cool. I just want to get you to feel for kinetic energy now that we know where it came from in 5.0. Let's try another one. Try to build our conceptual understanding of this. So you have kinetic energy. Example, you have 2 blocks. One has twice the mass of the other. So let's say 2 kilograms and 1 kilogram. And they're both sliding on a frictionless floor, and they both have the same kinetic energy. Which object is traveling faster? The 2 mass object or 1 mass object, or do they have the same speed? Okay, so they're both sliding at the same kinetic energy. Which one is traveling faster? Try it out. Pause the video now. Okay, so we're back. Let's pick a number for, excuse me, kinetic energy. Why don't I just say 4 joules? We'll just pop it in the head. So let's say the top car has, since they have the same kinetic energy, they both have 4 joules of energy. And the top car has 1/2, and its mass is 2 kilograms times the velocity squared. Okay? The bottom car is 1/2 times 1 kilogram times velocity squared. All right? So the 2's cancel out. You get 4 joules divided by 1 kilogram, and that's equal to V squared. Square root both sides. And what you end up getting is this one has a velocity of 2 meters per second. All right, over here, this is 1/2, so that's 1 kilogram divided by 2. Multiply it on the other side, you're going to get 2 times 4 joules over 1 kilogram. We're going to square root this. And we'll square root both sides, and so what you have is 8, which we're going to square root that. which is going to be 2.83 meters per second. Okay, so this is 2.83 meters per second. So essentially, because the smaller object has less mass, it has to be traveling faster in order to have the same kinetic energy as a heavier object that has the same kinetic energy. So the answer to this one is A. All right. Now, let's talk about potential energy. Now, I talked a little bit before in 5.0 that potential energy is called potential energy is because the force is independent of a path. And when we talk about potential energy due to gravity, here's the deal. So let's say you throw a ball to a friend. It goes here, and then it's coming here, and then it's coming here, and then this is where it hits its maximum, and then it starts to come back down towards your friend. And then your friend catches it with the same speed that you threw it up at. Okay, so here's your friend over here. So you threw it here and here. Now, at all of these points, when we talked about this in motion, especially in two-dimension motion, I think that was, I want to say somewhere in like 2.8, or actually, that was, no, 3.0. Anyways, my point is, the whole time it's in the air, and I'm saying air, but let's say it's in free fall, gravity is pulling straight down on it, right? The same amount, no matter where it is. So the gravity is pulling straight down on it. Now, look at the path it takes. It is taking this path right across here. But that doesn't matter because that gravitational force is pulling down no matter which path it takes. If you threw it straight up, gravity would be still pulling it down. If it was falling down, gravity would be pulling it down. If it was moving to the right, moving to the left, moving up and to the right, moving down and to the right, up and to the left, down and to the left. No matter what, gravity is pulling down on it. So that's what they mean by this is potential energy is caused by conservative forces. And a conservative force is independent of path. Okay, doesn't matter which way the object is moving, that force is going to be acting on it in the same direction no matter what. Okay? So that's what a conservative force is. All right? So really, just to get to the point of it, is gravity is the weight of the object times its height. That's its stored energy. Okay? And so I think of potential energy due to gravity as just the energy of height. All right? So I just call this the energy of height. The higher up something is, it has more potential energy due to gravity. Okay? Now let's test your understanding of potential energy due to gravity. Okay. Which requires a greater change in gravitational potential energy? You're going to lift a 50 kilogram sack of potatoes 1 meter up, and your friend is going to take this same is going to take a sack that is half the amount, but he's going to raise it 2 meters up. Which one has a greater change in potential energy? So think about this for a second. The 50 kilogram sack moving 1 meter up, the 25 kilogram sack moving 2 meters up, or they have the same change in potential energy. Try this out. Pause the video now. Okay, well, potential energy here due to gravity. So U sub G, that's going to be equal to, well, U sub G is equal to mgh, right? It's the energy of height. So we're going to take the weight of the object, which is going to be 50 kilograms times 9.8 meters per second squared, and we're going to multiply this times a height of 1 meter. This other guy over here, this potential energy, is going to be 25 kilograms times 9.8 meters per second squared times 2 meters. When you multiply this all out, 9.8 times 50 times 1, 490 joules, right? So this is a Newton times a meter, and a Newton meter is a joule. So this is 490 joules. Well, over here, this potential energy is going to be 25 kilograms times 9.8 meters per second squared times 2. That is also 490 joules. So whenever you're lifting weights, you could lift a heavy weight 1 meter or lift a lighter weight twice the distance, and so you will be burning the same amount of calories. Okay? That's what this is saying. All right. Let's try this over here. So here is another question. You're going to be using the picture below. You're going to rank the amount of energy expended from largest to smallest while moving a weight up from the bottom to the top. Okay? So we're going to rank A, B, and C from largest to smallest, the amount of energy used to take an object from the bottom here to the top. Here, you're going to push, and the top meaning 3 meters up. Here, you're going to be pushing this along a 5-meter path up. Okay, and here, you're going to put it up. You're going to bring it up 1 meter, take a break, get a Coke, put it up here another meter, take a nap, and put it up here finally, and you're done. So they're all getting to a height of 3 meters. Which one are you going to expend the most amount of energy in moving it up? The one that is the direct path, one along this 5-meter path, or one where you get to take little breaks? Try this out. Pause the video now. Well, in this case, let's give this guy 2 kilograms, right? So this is 2 kilograms. The weights are all 2 kilograms. And this is 2 kilograms. All right. Now with energy, it is path independent. It's a scalar. It means that it doesn't matter what happens in between here and here. It just wants to go from beginning to end. And so that is why potential energy due to gravity, which is going to be 2 kilograms times 9.8 meters per second squared, and this is it's gonna go from 0 meters to 3 meters. So 2 kilograms times 9.8 times delta H. Okay, and when you look at this is going to be equal to 2 times 9.8 times 3, 58.8. So here, you're going to spend 58.8 joules of energy, which are calories, 4,128 calories. Times this. So that's the kilocalories. So going on to here, well, this is also path independent too, because it just goes with the starting position. So 2 kilograms times 9.8 meters per second squared. And its starting position here is 0 meters high. Its ending position is 3 meters high. So when you calculate this guy, you're going to get 58.8 joules. It doesn't matter the path it took. All it just goes is where you started and where you ended. It doesn't matter that you took this long distance. And finally, you guessed it, this last one, it's the same thing. Even though you took all those little breaks, and it took you probably 2 hours to do this, because you're a busy person. It doesn't matter. You started here, you ended here. It doesn't matter how long it took. It doesn't matter if you took breaks. You're still using the same amount of energy to raise it up. So you're still expending the same amount of calories to raise it up that height. Okay. So ranking these from largest to smallest, they're all the same. Okay. So all of these are equal to each other. All right. So hopefully you know a little bit about potential energy due to gravity and how it's path independent. Potential energy due to a spring is also path independent. All right. It's also caused by a conservative force. So what that means is if you pull a spring, that spring is going to want to restore it back to the equilibrium position. If you compress that spring, it's going to want to snap back to that equilibrium position. So no matter which way it has moved, to the right or to the left, it's always being restored back to that equilibrium position. Again, this is path independent. Okay, so potential energy the reason why a spring is a conservative force is because it exerts the same force no matter if it's being compressed or stretched. It's again independent of path. Okay. Now, we learned from forces that it has a spring constant K, which is how stiff the spring is, and that's in newtons per meter. And we also had learned that delta X is how far it's compressed or stretched. It's a distance, not a displacement, but it's a distance from that equilibrium position. Okay. Mu sub S is also always positive, just like the other potential energy due to gravity. In our class, we're going to use potential energy due to gravity and potential energy due to a spring. Those are going to be positive values, and also kinetic energy. We're going to make sure those are positive values. Okay. Now, just like potential energy due to gravity, potential energy due to spring can add or take away from kinetic energy. And it is at a yin-yang with kinetic energy, right? So if you pulled a spring and let it go, you've got a potential energy that you've added to it, and that potential energy decreases as the spring pulls the object, speeds it up until it reaches its maximum speed at the equilibrium position. So kinetic energy is high, potential energy due to a spring is low. Or potential energy due to a spring is high, kinetic energy is low. All right. Now, let's talk about kinetic energies and build those conceptual understanding. Okay. So, which one of these, A, B, or C, has the most potential energy given, given that the equilibrium position is 0? So over here at B, you pulled it a distance to the right, which is positive X. At C, you compressed it a distance negative X. And here at A, it's just at the equilibrium position at X is equal to 0. So which spring has the most potential energy given that the X equals 0 is equilibrium position? Try this out. Pause your video now. Okay, so going right here, potential energy due to a spring, that's going to be equal to 1/2 K and X squared, right? which that's a delta x, but let's just keep it simple here. K, and its value here is 0 because it's at the equilibrium position. So this potential energy due to a spring, I should put an S here, due to a spring is equal to 0. Over here, you've got it pulled to the right. So this is mu sub S. And again, I should have made sure that I used a delta x here. It should be delta x squared. So this potential energy due to a spring is going to be equal to 1/2 K. And its delta x is going to be, it's been displaced a positive x that we're going to square. So its value is just going to be 1/2 kx squared. All right, over here, this last guy, its energy due to a spring is going to be equal to 1/2 delta x, which in this case has been compressed a distance negative x. Well, we're going to square that one too. So this is going to end up being 1/2 kx squared. So which spring has the most potential energy? B and C are equal to each other, and both of those are greater than 0. Okay. All right. Now, again, I just want to reiterate the reason why springs and spring force and mass times gravity or weight force are path independent. They're considered conserved forces. It's because they are independent of the path. Okay, so over here you can see for a spring, no matter what, that spring is trying to restore. It's applying a force to your hand, trying to pull your hand back to the center. And over here, it's trying to restore it back to 0. Over here with potential energy due to gravity, we had talked about if you throw a ball to your friend, no matter what, gravity's pulling down. Over here, when that ball is being pushed up this ramp, no matter what, gravity is pulling it down. Okay? So that's the reason why these things are considered path independent. That's the reason why potential energy force due to gravity and force due to a spring, that's why they're considered conservative forces. It doesn't matter the path. And so that's why they're labeled conservative forces and their potential energies. Okay? Now, we talked a little bit about work in 5.0, and where work is equal to a force times its displacement. In other words, if you have a function of a force and you integrate that with respect to distance, x, or a distance s, then that work function is that force causing an object to have a displacement, which is going to be speeding it up or slowing it down, or it's going to be raising it up a distance, or it's going to be stretching it. So these work forces transfer energy between kinetic energy and potential energy. Well, can do that, but work is the result of all these different transfer of energy between systems. Okay? So an interesting thing about that, aside from spring forces, all contact forces are considered non-conservative forces. So aside from spring force, all contact forces are path dependent. Okay, so if you push an object along a distance here, so you have a mass right here and you begin pushing it with a force horizontally, that is going to move it to the right along that path. And the further the more it moves that distance, the more work you are doing. Okay, so if you've ever done sled pulls or sled pushes, that is what I'm talking about. They are path dependent. And what that means is if you have a dot product right here, and we studied dot products in lectures 2.2 and 2.3, okay, that the force and the displacement have to be in the same directions, okay? So we had talked about how if you have a force here and a displacement here, and let's say there was another displacement upwards, right? That a dot product, F dot dx, okay, is going to result in F delta x, right? But if you try to do a dot product along a y direction, which is perpendicular to it, you get 0, okay? And this does make sense. If you want an object to move to the right, some part of that force has to push it to the right. If you want an object to move to the right, but you're pushing it upwards, it's not going to be moving to the right. It's going to start moving upwards, right? So it's kind of, you know, totally makes sense. It's just common sense in a way, okay? So that is the basics of work, but we're going to go ahead and get into it a little bit more. Now, in your book, they talk about positive and negative work. And I always felt from reading these books, both books, that they should get more into what does positive and negative work mean. So suppose you had a displacement vector, a gust of wind is pushing a person on one of these sail boards to the right. So they're moving to the right and their force vectors to the right, okay? So here's what I mean by positive and negative work. So work, again, is equal to force times displacement. Let's not worry about the cosine so much, okay? But those are vectors, okay? So if a force is to the right, it's got a positive direction to it. And if a displacement vector is also to the right, that's also a displacement, that's also a vector, right? Well, force is equal to mass times acceleration. And displacement, well, displacement is a velocity. Really, it's what gives velocity its vector. So in other words, we could say that displacement is a positive velocity vector to the right, and that force vector is analogous to a positive acceleration to the right. Well, we learned that a positive velocity and a positive acceleration, that is speeding up, okay? Okay. In other words, when we talk about its work over here, we're going to have a positive force times a positive displacement. That's going to be equal to a positive work. So, and since work is equal to a change in kinetic energy, where kinetic energy final minus kinetic energy initial, that final velocity, in this case, if it's speeding up, is going to be larger than the initial velocity. This is a little initial velocity. So if your final kinetic energy is larger than your initial kinetic energy, you are also speeding up in this case. So in other words, when those two vectors are pointed to the right, that is going to result in something that is speeding up, and that is called positive work. how I think about that is you're adding kinetic energy to the system. So positive work is adding, misspelled adding, kinetic energy to the system, to the object or system. Okay. Similarly, if you have a displacement vector to the left and you have a force vector to the left, well, again, those two things are essentially just a negative velocity vector and a negative acceleration vector, right? Which is speeding up, but in the negative direction. So here we have our work function, which is going to be equal to a negative f vector times a negative displacement vector, and that is going to also result in a positive work, which is speeding it up, which means it's going to be adding kinetic energy to the system. So as long as those force vectors and displacement vectors are in the same direction, you're adding kinetic energy to a system, and that is what positive work means. Okay? Now, another way of seeing this, what negative work is over here, is when you're moving to the right, but the force vector is working opposite your direction. So if you are moving to the right and you have a positive displacement, but something's pushing you to the left, which is going to be a negative force, well, that essentially is going to be a negative acceleration, but you have a positive velocity vector. Okay, displacement, again, displacement and velocity are the same thing. Well, in this case, you're going to be slowing down. All right, so this is slowing you down. All right, and when we're dealing with the work here, we have work and we have our negative force vector times our positive displacement vector. Well, negative times a positive is a negative. So in other words, your kinetic energy final, in this case, which is your delta K, your kinetic energy final, if you're slowing down, your final velocity is going to be small, but your initial velocity is going to be large. Okay? So, in other words, you are subtracting. So negative work is taking away kinetic energy. Okay, you're taking kinetic energy away. So if you're on a chair moving towards me and I want to get you to stop, I push opposite the direction you're moving, and that slows you to a stop. But if I want to speed you up, I got to push you in the direction that you're moving, and that will then speed you up. So I'm adding kinetic energy to that. Okay, I'm going to just, to be clear, I'm going to write the opposite. Suppose you're moving to the left, okay, which is a negative velocity vector, but your force vector is to the right, which means you have a positive acceleration vector. This is also going to be a negative work, right? Correct? So you have a positive force vector times a negative displacement vector. Well, that's also a negative work, which is going to take away kinetic energy from a system. So somebody's moving to the left, you push them to the right to slow them to a stop. You take their kinetic energy. All right. Now, if you look at this from the perspective of energy versus time, if somebody's moving at a constant velocity, okay, and let's say they're moving at a constant velocity across the system, 1/2 mv squared, okay, and so their initial kinetic energy is equal to their final kinetic energy, okay, so that constant velocity is going to look like this. Their energy is not going to be changing across this 6 seconds. If you check their kinetic energy in the beginning, it's the same thing as it is in the end. So this is where there is no change to their energy across time. Okay? So that is a constant energy, okay, from the system. But if somebody was not moving, if somebody was not moving, and then you started adding energy to them, so they were not moving, and then in the end they were moving, you've added energy to that system, all right? So the slope of that line is positive. So this is what positive work looks like, all right? That's positive work. This is work is equal to 0. There's no outside forces changing your energy, right? If you're moving to the right and you're sliding across ice, and there's no friction, there's nothing to speed you up or slow you down, you're going to move like that forever. Okay, you need an outside force to slow you to a stop, which is Newton's first law. Now, if the slope is negative, okay, so let's say you had a kinetic energy, and then somebody brings you to a stop across that distance, okay, well, you're taking their kinetic energy. Notice the slope of that line is negative, okay, all right, so this is indicative of negative work. When you have a slope in an energy versus time graph, when there is a slope, there's either a force, an outside force adding to that or taking it away. However, when there is no change in energy, okay, then that work done is 0. Okay, so that's another way of interpreting energy. All right. Now there is, again, something interesting about that work function, okay? And we talked about dot products, okay? So if you are pushing an object to the right, okay? Actually, let's say you're pulling an object up and to the right. This force, which is going to be the F, if this is F sine of theta. That is a waste of force. This is a waste of energy. Okay, so this is, I should say, loss. This is a loss. Why did I start with a Z? L-O-S-S. Okay, only this part of the force that is parallel to your displacement is going to be something that speeds you up or slows you down, as long as your displacement vector and your force vector are in the same direction. Again, we're talking about acceleration and velocity. Now, back in motion, we had learned when your acceleration vector is perpendicular to your velocity vector, okay, that doesn't do anything. All it does is it changes your direction, okay? So this neither speeds you up nor slows you down. It just changes your direction. Well, in this case, this force vector is not going to speed you up or slow you down. It's just possibly going to change your direction if it's allowed to be moved off the floor. But assuming the object can't move off the floor, then the only part of the force that is going to be responsible for moving to the right is one that is parallel to its displacement. And so that's the reason why we have a dot product here. And again, if you need to review dot products, that is in 2.2 and 2.3. So that's for the dot products. Okay. Now, another type of contact, most contact forces, all contact forces outside of work, outside of spring forces, are considered non-conservative. So they can add energy to a system and they can take energy away from a system. The one that we will be dealing with the most with is friction. Okay. We also just have outside forces, you push an object, speed up or slow down. But another type of work, and I want to kind of look at this separately, is friction. So even though friction is a force, okay, we're going to be using it so much in this class, we should probably talk about it. Okay, again, friction is a contact force, and it is path dependent. All right, so friction only works parallel to the surface and in the direction of the displacement. Okay, so it is path dependent, and so therefore it is a non-conservative force, which means it's going to be adding energy or taking energy away from a system. If we have kinetic energy, kinetic friction, okay, I'm sorry, going back to this, work being force times displacement, and friction is mu sub k or mu sub s times that normal force times the displacement. Okay, so it's the friction force times the displacement. So you have kinetic friction and you have static friction. Now there's two ways to look at this. Okay, kinetic friction will always consume kinetic energy. Okay, so if an object is moving to the right, what we had learned, if an object has a positive velocity vector, kinetic friction works opposite that, right? So mu sub k times the normal force, that works opposite your velocity vector. So kinetic friction will always slow you down, right? Since this is also equal to mass times acceleration, kinetic friction will always slow you down. And if your velocity vector, which is analogous to a displacement vector, okay, well, what that means is this is going to result in a negative work. Okay, you've got a negative friction vector and a positive velocity vector, or a positive friction vector and a negative velocity vector. Either way, you're going to have a negative work, which means kinetic friction always consumes your kinetic energy. For example, you push a cardboard box on the floor and let it go, it'll be brought to a stop by kinetic friction. That kinetic friction will consume its kinetic energy. Okay. Now, static friction can speed you up or slow you down. Okay, so static friction, which a car tire and your feet work by static friction. When you push against the floor backwards, static friction is what pushes you forwards. So to speed yourself up, you get set and you push against the floor, static friction pushes you forward. That speeds you up. Static friction can also slow you down. So if you're running and you need to run to a stop, or a car needs to be brought to a stop, the tires will slow. You hit the brakes, and the car tires are pushing forward against the road, which means static friction is pushing in the opposite direction that it's moving and slowing you down. And what we had learned is that static friction tends to work in the same direction as your acceleration vector. Okay, so that one you have to really think about. It could speed you up or slow you down. But we are mostly going to be dealing with kinetic friction in our class. So most of the time when we talk about friction there's a rough surface, or they're going to be referring to a kinetic friction. Okay, so I wanted to point that out. Now let's talk about power. Okay, so when we were first talking about energy, potential energy due to gravity, sometimes some students may think you consume more energy by lifting it straight up versus rolling it up a hill versus lifting it, taking a break, lifting it, right? What that means is, I think you're thinking about time, okay? And so power, which is in watts, okay, power is the amount of energy, change in energy over the change in time, okay? So even though you're lifting those three things, and I want to, since I'm referring to it, I'm just going to grab it real quick. Hold on. Okay, so I went and grabbed it, brought it over. Obviously, if you lift something straight up and put it up on top of a pillar 3 meters high, you're going to do that very quickly. And this one will take a little bit more time, and this one can take all day if you want. So A will be faster than B and versus C. Well, power is how we think about it's basically it's effort, right? So if you do CrossFit, they also, or those high intensity workouts, power is that intensity. Okay, and what they mean by that is, even though you're burning the same amount of calories, if you do it, since delta T, if you do it quicker, that power output is going to go up. Okay. However, if you take a long time to do something, power is going to drop. And you're doing the same thing. So you're lifting an object 3 meters high, but depending on how quick you do it, that will be your power output. Okay. And so that is intensity in exercise science. Okay. So high intensity workouts, they're actually talking about power. It's not how many calories you burn. You could be burning the same amount of calories, but the one that takes more effort is going to be the one that is less time. Okay. Now power is a joule per second, which is what we call a watt. So 1 joule per second is 1 watt. Okay. So when I get billed at the for my power consumption, my house is using so many watts. Yeah, that's what they're talking about. Okay. So let's talk about our understanding. Let's test your understanding of power. Okay. So you and I are working out right next to each other. Okay. And you are going to lift a weight up. A weight is sitting on the floor. And let's say you lift a 1 kilogram weight, 2.2 pounds up 1 meter in 3 seconds. And I do the same in 6 seconds. Who burned more calories? Who had more power? And let's plot those on an energy versus time graph. Okay? So go ahead and answer this question and try this out, and pause the video now. Okay, so who burned more calories? So let's use red as you. So you're adding potential energy due to gravity. So you're taking 1 kilogram, you're raising it up 9.8 meters per second squared, and you're raising it up 1 meter. Okay. In fact, we're both doing that. So overall, both of us are basically burning 1 times 10 times 1, about 10 joules. Okay. So they're both about 10 joules. Okay. But so we're both burning the same amount of calories. But who is doing more, who has more intensity? Well, for you, that's power. And this is going to be your energy over time, your change in energy over change in time. Okay, so from 0 to 10 joules. And you are doing 10 joules over the period of 3 seconds. Okay? So that is your power, which is roughly, what is that? Going to get to, what is it? 10 divided by 3, 3.333. I probably should have known that. Okay, so your power output is going to be 3.33 watts. My power output is going to be 10 joules divided by 6 seconds, which is going to be, I probably should know this, but I don't trust myself either way, 10 divided by 6, 1.67. So my power output is going to be 1.67 watts. What that looks like, if we plot that, for you, you start with 0 energy and you get to 10 joules over the period of 3 seconds. Okay? Now, I'm getting to 10 joules as well, but for me, let's try that again. If you look at this, I'm doing it over a longer period of time. And if you look at the slope here in energy versus time, that is power. This slope right here, at any point in time, that slope is power. And that for me is 1.67 watts. And your slope is going to be, so this is your slope, straight line, any point in time. So your slope is going to be your power, which is 3.37 watts. Okay? Right? So when we're looking at energy versus time graphs, we're getting a lot of information. Okay? We could tell that there was work done and that both of these slopes are positive, so we're adding energy to the system. We're both adding energy to the system. Okay, so we're both adding potential energy to the system. But the slope of that line is your power. That's your power output. If it's positive, you're adding energy to the system. So in a way, we should actually think of this as power input, how much power you're putting into the system. If the slope is negative, that's your power output, how much power you're taking from a system. Okay, so if the slope is negative here, which is going to be a negative power, that is output. You're pulling from the system, taking energy away from the system. While a positive slope is you're adding energy to the system. A zero slope, again, is you're not adding or subtracting energy from the system. You're doing nothing. So positive work, negative work, and zero work. That also tells you your power. So they're very useful. Just a little side note, the area under these lines are related to action, which is S. If you want any information in the PowerPoint that I have, if you click on this, it sends you to PBS Spacetime, which there's a great lecture about principle of least action. So action is this. So these are both related to that, but specifically action is a Lagrangian function, which is the difference between your kinetic energy and your potential energy. Okay, this is important for later on. Okay, not in this class, but much later on when you get into graduate studies. A lot of what I remember doing is Lagrangian functions and computing action, which is high level computation. So energy is important because it leads into action, and action crosses from large planetary objects to also is predictive to quantum level. So it's a very important concept, but it's very complex, and we're not going to do it in our class. So we're not really going to be concerned about the area underneath this line in energy versus time graph. Okay. All right. Finally, with efficiency. So with efficiency, that is the amount of energy being put out from a system or brought into a system over the total amount of is it the energy output versus the energy input. So if you take the total amount of energy being spent by a system over the total amount of energy that you're adding into a system, so this is like fuel efficiency. So this is kind of how far you go, which is work is force times the distance. So that could be considered your mileage over your amount of gas. So this would be like the gas in your tank. Okay, that's how I think about this. So if you burn gas, how much energy is that? And then if you compute how far your car is driven, and this is the weight of your car, if you think about it that way, that is your fuel efficiency. Okay. All right. Well, we are done with 5.1. I hope you learned about kinetic energy, potential energy due to gravity, potential energy due to springs, and what work is. Now, in the next part, 5.2, we're going to get into the calculations of those. All right. Thank you very much.